Welcome everyone. This is our 102nd live stream geometry. We have two other people here with us now, and today I'm going to go over problems from the IMOC. So it's a contest in Taiwan. This actually happened last year. We think a couple months, maybe around September. So yeah, I'm taking a break from doing the geometry discussions and problems Discord server, and I wanted to try doing something else this time. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So with that, I will share my screen. Just a second. All right, so here is the first problem. We start with any point P inside of a triangle ABC, and we draw the circumcircle of ABC. Oops, not that. BP and CP, we see where they intersect the sides. E and F. Let's draw one more ray, because we're going to want to see where this meets the circle. So yeah, I feel like we've done a couple problems like this where you see where two of them meet the sides and the other one meets the circle. So this is going to be E and F, and this is going to be X. And then we see where ABC and AEF meet the circle. So that gives us a spiral similarity. So SFE is similar to SBC. And P is on BC such that PT is parallel to EF. It's kind of interesting. Let me see if I can make this look a little. I don't know if you have to extend BC. Maybe you do. Yeah, I think you do have to extend BC. Probably, I don't know, due to harmonic conjugates or something. We'll figure it out. So this is T, and we're saying that so we draw the midpoint of BC. Then we want to show, we call that M. Whoops. Oh, I think that was it. We want to show STXM is cyclic. Let's check that out. Looks like a nice problem. Could be easy, hard to tell. Let me hide a little bit more. All right. So we have this, this, and this. And then we have this and this. So BMC infinity is harmonic. Maybe we could project that onto EF somehow. So obviously, thinking about using projective geometry. It's just a matter of how to do it. So we could project like F, E, the point at infinity, and some other point onto BC. I just don't know what that other point is. Maybe this point right here. And looks like Leia's joining. All right. So what's a good way to do this? Let's think. Maybe we could work backwards. If this is cyclic, can we use, hey Leia, so thanks for joining. This is our first problem. If this were cyclic, what could we do? Could we use power of a point? Can we use power ratio lemma? Let's think what the best way would be. An angle chase. Kind of thinking power of a point might be good. It's just figuring out the right one to do. Let's see.
We can get rid of point T by projection.
Okay.
If you intersect S X with BC,
Okay.
then we would want to show that power of a point thing.
All right.
But now, if you add in the midpoint of EF.
Okay. So now we use the midpoint of EF.
Yeah. Then we should prove that those three are collinear, D, P, and G.
Okay.
So let's suppose that it is true for now, to see how it finishes. You will have then that BC dt is harmonic.
BC
So there is
okay.
BC dt, and then there is a well-known lemma that when you have that harmonic bundle and you take the midpoint of BC, then dm times dt is dB times dc.
Okay.
Which will be then dx times ds, and that'll finish.
I like it. I knew there had to be some harmonic thing where you use the midpoint like that. Okay. So we have to show G, P, and D are collinear.
Yeah.
All right. All right. And yeah, that seems like such a general fact, like for any point P that holds true. So it's interesting. So if it were true when you projected through P Well, no, yeah, I'd just be going in circles then. But G corresponds to M in the spiral similarity. I wonder if that helps. So SFE is similar to SBC.
Where does that spiral similarity take point X?
How do I figure that out? Let me see. So I think is it kind of just like I draw SP and I see where it meets it? I think. Not sure if that does it.
Yeah, I think it is important to see where D and X go under the spiral similarity.
Okay. So yeah, this almost makes it look like P lies on the circle, which isn't true. So let me draw it a little different. Maybe something like that. So yeah, SFE. So angle SBX is BAX is F8. So yeah, I think it's kind of like I would look at in triangle SFE. I would kind of draw this point right here. Does X correspond to this to H and B corresponds to I? I think that might be the case because angle FSH is FAH is BAX. So I think that's true. I think H goes to X and I goes to D. And we want to show G, P, and D are collinear still.
I think by some symmetry we would have a PM and I are collinear. It just looks like it.
Yeah. I wonder if it's cyclic. This. No. But yeah, it looks like PM and I are collinear. And that would mean the cross ratio BDMC is the cross ratio EGIP. If we could show, well, that's true just by ratios, right? Because, well, actually, like if we could show the cross ratio BDMC, well, that wouldn't be enough to show that both of them are collinear.
Yeah, you would have to show one and then you could show the other. If that,
Yeah.
I mean, we know the cross ratio is the same just by spiral similarity, but we don't know one. It looks like it's just symmetric. It's like the same problem, showing MIP and GPD are collinear.
Yeah.
It's as if you wrote the problem with respect to a different triangle.
Yeah,
The
it's like they're
difference.
the same. It's like equivalent. Yeah. If you yeah, I see what you're saying.
Also, can you check that ID is parallel to AP? It looks like it.
All right. Yeah. Let me use the. Oh. Yeah, it sure looks like it. I could check it just by doing this, but yeah.
Oh, I think we can actually prove that. Maybe. Yeah. Can we show that Fm over Me is Bd over Dc? I think we can show that, right?
Say that one
Yeah,
more.
that is by spiral similarity. I was just looking in my picture, sorry. In your picture, Bd over Dc is Fi over Ie.
Yeah, that's obvious by the spiral similarity.
Yeah. Okay, so then we can use like a more general. Actually, we don't have, but we can just use the fact that about these spiral similarities to see that SFB is similar to SID.
Okay, because SFP,
SFB
SFB. Okay.
is similar to SID. So you could get angle SDI. It is equal to SBF.
Yeah. I see what you're saying.
Yeah.
Is SBF, which is SBA, which is SXA. Okay,
Yeah.
so we know this is parallel. It's an interesting observation. Yeah, I guess you could also just say I corresponds to D and H corresponds to X. So SID and SHX have to be similar, and then they're parallel. So yeah, if they were collinear, then yeah, TBDC would be harmonic. Yeah, can we use the parallel somehow? So so we want to show GP and V are collinear.
Maybe we add the midpoint of AP, then we get Gauss line.
Okay, so we have the midpoint of AP, and we could use a Gauss line. That's interesting. Sorry. It looks like these meet on the circle, and I don't want to make it look like that. So that thing that looks okay. Okay, so yeah, we want to show GP and D are collinear. Something like if we were to bash it, which like we could try to show angle GPE is angle BPD, and this is like a median in triangle FPE.
You could use trig.
Yeah.
We would want to show that sine of BPD over sine of CPD is equal to P over PF. So it would all come down to length calculation, since you can calculate sine of BPD over CPD.
How, let's think, how would we calculate that?
Sine of BPD over sine CPD is like BP over PC times BD over DC.
Okay.
Something like that. Maybe I flip the fractions, but yeah. Then the only tricky part would be BD over DC.
Yeah. Figuring that out.
But maybe we could use a trig again to do that. I think this can be trig bashed, since we could use the exact same calculation for triangle BSC.
BSC?
BSC.
Okay.
And you could say something like BD over DC is like sine of BSD over sine of DSC times like BS or SC.
Okay.
And both of those are things we know, since BSD is like BAP. Those two angles are the same. And SB over SC is by a spiral similarity, just BF over CE.
Okay. So I could, okay, so we want to show, we want to find the ratio of sine EPG over FPG. And that, is that like FP over PE or PE over FP? Is that it?
Sine of EPG or sine FPG is PE over PF.
PE over PF. So yeah.
That is a nice quantity.
And then to find that, we kind of have sine PAE over EP.
No, I would leave that as it is for now. PE over PF is pretty nice.
Okay.
And then we would want to find sine of BPD over sine CPD, and what we get for that should be PE over PF.
Yeah.
So we would want then, I'm not sure, it is like, is it PB over PC times BD over DC or some fractions of those flipped? I can never remember how it goes.
So yeah, so the area of this, the ratio of the areas of these two is BD. So BD over DC is the ratio of the areas, which is BP sine this angle over CP sine this angle. So yeah, I think it would be think it would be the other way, BD over DC times CP over PB. But yeah, I can write it out. So yeah, I think we have enough for a solution with a little bit of trig. Okay. So let G and M be the midpoints of BF and BC. And label I, H, and V as shown. So we're going to try to show GP and D are collinear. So sine EPG over sine FPG. So yeah, I'll write it like this. So the area of EPG over the area of FPG. G. And that's equal to EP sine EPG over FP and this means that EP over FP equals sine of EPG over sine of FPG. All right. Or actually it's the other way, right? Yeah, I think it's the other way, right? Is that right? I think so. And then we have BPD and CPD. So we have BD over CD is the area of BPD over the area of CPD. Which is equal to BP sine BPD over CP sine CPD. And this implies that sine of BPD over sine CPD is equal to BD over CD times CP over BP. Okay. So, and then this bottom piece, CP over BP, forget, I think you had an idea for that, right? BD over CD we can calculate because that's sine BSD. Actually, let me think about this.
Calculate BD over CD. CP and BP is like an okay quantity.
CP over BP?
Yeah, idea is like to calculate everything in terms of ABC, triangle ABC and point P.
Okay. So yeah, So yeah, I'm trying to think where we go after this.
We use the same thing for BCS.
So okay, BCS. So I mean BD over DC is FI over IE. I don't know if that.
Yeah, we don't really care about point I in this solution.
Okay. So BD over CD, you're saying that's like BS over SC times like sine BSD over CSD or something like that. Which would be
Yeah.
sine BAP over CAP. But how do we get rid of the BS and the SC then? That's kind of what I'm wondering.
You just have spiral similarity. BS over SCE is BF over CE.
Ah, okay. And I missed that. All right. So BD over CD is whoops. It's so yeah, it's kind of like what we did here. So it would be I'll just write it all out with areas, why not? So BSD over CSD. So BD over CD is equal to that, which is equal to BS sine BSD over CS sine CSD. And this is equal to BS over CS is BF over CE. So this is BF over CE times sine BAP over sine CAP. Actually, I think if I do this, it'll work better. There we go. So then we combine these two. So we have BF, CE, FP. Okay, so it might just be like a law of sines that finishes it off. So so yeah, we want to show that if you substitute this into here, then it would equal this. P.
Maybe use the same thing for triangle AFC now, since you would have those two angles, which we have sine, so it would come down to some Travis theorem or something like that in the end.
Okay, so you said triangle, what was the triangle you said?
AFC.
AFC. So BF, I think there might be. So if we do the law of sines on BFP, we have sine of this over BF is sine of ABP over FP. So yeah, here's what I think I'm going to do. So we have sine of FPB over BP is equal to sine of EPC over EC. No. This is a separate statement. So this is equal to sine ABP over FP. And this is equal to sine ACP over EP. And then also we have sine ABP over AP. So yeah, I think if we do one more law of sines, it kind of finishes it. So sine ABP over AP is sine BAP over BP. Oops, I want to make these separate statements. This would be sine BAP over BP. And this would be sine CAP over CP. So I think when you combine all these, you get to where you want. So if you combine all this above information, I think you get that the ratio of this sine is equal to the ratio of this sine. I'm just guessing it'll work out. So FBP. This should be sine FPB. Oh, this should be BF. Yeah. So I'm just gonna assume it works because I'm lazy. Combining the above sine FPG or sine of EPG is equal to sine of BPD or sine CPD, and that means that
flips the ratio.
Oh, you're right. So yeah. This means that G, P, and B are collinear. And then projecting through P onto BC, we have -1 is equal to EFG infinity. Which is equal to BCMT. And that means that dm times dt equals dB times dc. dc, which is equal to dx times ds, and that implies that STMX is cyclic, and that means that STX passes through the midpoint M of BC. All right. So I guess we have enough room for it like right here, so I can just leave that right here. Interesting. I'm sure there's a way to do it without all this trig, but it's kind of an interesting solution. All right. So here's the next problem. So thanks for that. We have an acute triangle with circumcircle omega, and we draw a line through A perpendicular to BC, and it meets the circle at B. Then we draw two circles centered at B and C, and the radii are BD and CD. We see where they intersect AB and AC. So we have this circle and this circle. So really just, let's see. So it's kind of interesting because these circles are going to intersect here because we know at the orthocenter. So basically, we let H be the orthocenter, and then basically, and not only that, this is going to be the CH and E are going to be collinear. So just so I don't get the names of the points wrong, this is E, this is F. I don't think they ever use G and H, but or G and I, but basically these would be collinear, and these would be collinear because the reflection of the orthocenter over each side lies on the circumcircle. Okay, so we have these cyclic quads, a lot of circles. So let K be the second intersection of AEF and gamma. So that's AEF. So that's not a circle we see very often. So that's K. And let those two circles intersect KB and KC at P and Q. Oops. So interesting. There's a lot of information in this problem, I feel like. So this is P, and this is Q. The circumcenter of BPQ is O. So a lot going on here. We want to show that K, O, and B are collinear. This is just so random. Let's see the best way to draw. I think if this is like a tall triangle, it makes it easier to draw. We'll just shrink the figure a little bit. But I kind of like that. Let's see. Yeah, the weird thing is, yeah, that circumcircle of AEF. It's not something we see very often. Like sometimes I wonder if So if I draw these points, I don't think that's the Q point, is it? Because that would make things a lot easier if it was. Oh, I think maybe it is. Like K might just be, yeah.
I think it is actually easy to prove.
Okay.
But it is Q point, and yeah, it simplifies things a lot.
Yeah.
So you'll just see that segments CF and BE, they're basically just BH and CH numerically. And you would want to show that E and F are corresponding points in similar triangles HB, J, and HCl. And that looks like quite obvious with
Yeah.
length, since we can just show that CF over CL, it is just CH over CL. And
Yeah.
that is equal to BH over BJ, which is BE over BJ. So we know that.
Yeah. Okay. So yeah, K is the Q point by that argument.
Also, I just noticed that PQ looks parallel to BC.
PQ looks parallel. Okay. So that, yeah, maybe we could do that with ratios. So like we could try to show KP over KB is KQ over KC. And I wonder if that's somehow obvious. So I think it's kind of the same as saying KB over KD is KC over CD.
Oh, but that is a famous theorem that KBDC is harmonic.
Harmonic. Yeah, I was gonna say it looks like harmonic. Okay.
It is you can prove it by one projection with after using radical axis theorem. You just see that AK, JL, and BC concur by radical axis theorem, and then you can project.
Okay. So then yeah, so that proves that PQ is parallel to BC.
Also, don't know if you noticed, but point O is not really important. We want to show that DK and DA are isogonal in angle PDQ. So here in this picture, the only like tricky thing left is handling this angle DPQ, PDQ.
Okay. So we want to show, what did you say was isogonal?
In order for us to have that DOK are collinear, then DO and DH would be isogonal.
DO and DH would be isogonal.
Yeah, since DH is perpendicular to PQ. So we want to show that DK and DH are isogonal in angle PDQ.
Interesting. Because yeah, we already know that DH is perpendicular, so if we could show that those are isogonal, that would solve the problem. Okay. Interesting. So, oops, that's not what I wanted. Yeah, I'm sure it's true. I'm just, yeah, just like to see it for myself. 8.6, and this should also be 8.6. I think it is. Yes. All right. Yeah, we got a lot of good information here. So, I mean, we know that DO and DH are isogonal. We want to show DK and DH are isogonal. I think that's what you were saying, right?
Yeah.
Yeah.
Also, we can kind of handle the angle QDH. It is just half of angle QCH.
Oh yeah, because of the circle. So yeah, that's a good observation. And QCH is half of angle ACJ. So it's like a quarter of angle ACJ.
So maybe the rest is just like an angle trace.
So that gives us QDH. And then how do we get ADK? Oh, ADK is just ACK. Yeah, it's just an angle chase. Yeah. Wow, this is easier than I thought. I guess GEO.
Yeah, which one was this? So it is like G1, G2.
I'm not sure. Let's see.
This was for sure much easier than the last problem.
Yeah. G4. So I guess that's, yeah, right before G5, but it was still pretty easy. Yeah, let's type it up. So I'll say label G, J, I, and L as shown. And then since the reflection of the orthocenter over each side lies on the circumcircle, then we have GPEHD, and IFQHD are cyclic. I don't even know if we need I and D, but oh well. All right. So we have this, and then we show that K is actually the Q point using ratios. So yeah, it's well known that KB, so let K prime be the Q point. Then basically we show, like, did we try to show KE over KF as KJ over KL? I'm trying to remember how we did this. So we had like, well, okay, the harmonic was to show PQ as parallel, but the Q point, I'm trying to remember what we did here. Oh, the Q point, we used that corresponding points. What is it? So in triangles HJB and so BHJ and CHL, E and F correspond to each other, and that's
Yeah,
how.
exactly.
Yeah.
So you just prove that BE or BJ is CF over CL, and that is obvious by lengths.
Yeah. So BE over BJ is CF over CL. That is obvious because so yeah, BE over BJ is BH over BJ. and that's CH over CL, I think it is, which is CF over CL. So E corresponds to F in those similar triangles. All right. EHJ, CHL. And once we know that, from there we have BEK is similar to CFK. So that means that, so
You can say then a spiral similarity takes E to F. That's
yeah.
the quickest.
So basically, the way we're doing this problem, we're letting K be the, we could let K prime be the Q point. So
It is actually not necessary.
okay.
You can take the spiral similarity, which takes like E to B and F to C, and that will be centered at K, and then prove that it takes J to L, which is also just obvious by these ratios and the correspondence. So you don't have to define K prime. Just say like that, and then say K is the Q point.
So spiral similarity at K takes it takes to or KEF to KBC. And it also and it also takes there's like two different, well, you could say KEB to KFC, and then it takes it takes J to L. So I'll say KEB to KFC. This also takes J to L, and that means that KAJL is cyclic. I think that's a fine way to say it. And obviously, I'll just throw H in there. I mean, it's obvious that H has to line that circle. So now we find the parallel using the harmonic quad. So it's well known that KBDC is harmonic. I can't spell. And that means that KB over BD equals KC over CD. And that means that KB over PB equals KC over QC. QC, which means that PQ is parallel to BC. And once we have this, so that means that DH and DO are isogonal, angle PDQ. P to Q, PDQ. There's a restaurant called PDQ in the US. It stands for People Dedicated to Quality. Then we want to show DH and DK are isogonal, and we were saying that's an angle chase. I'm trying to remember, because DHDQ is half of this, which is a quarter of AC ACH, and then K. How was I trying to say KD? Yeah, how do we find KDP actually? Maybe I don't know why I thought the problem was solved. Maybe it's not that easy. KDP. Is there some other point that this segment passes through? It almost looks like it passes through E, but I don't think that's true, because then by symmetry it should pass through F. So yeah, I got confused.
What is confusing you?
What?
What is confusing you?
Oh, so PQ is parallel to BC. Well, okay. We know DH and DO are isogonal. How do we know that DK and DH are isogonal?
Angle chase.
So we can find angle HDQ. How do we find angle PDK?
So I was thinking of something like this. PDK is BDK minus BDP.
Oh, okay. And then it is an
And both of those angles are quite nice to work with.
Okay. So I think that makes sense. So angle PDK is BDK minus BDP. And once we have that, that's angle BCK. Minus, yeah, what's a good way to say this? So, I mean, BDP is 90 minus half of KBD. All right, see you in a little bit. So BCK minus 90 minus half of KBD. Okay, so I'll leave that for now, and then let me calculate QDH.
No, you can calculate it more.
Okay.
KBD is just 180 minus KCD.
Okay.
Which you split up into KCB and BCD.
Okay, so this is angle BCK minus 90 minus 180 minus KCD over KCB over 2. Which is equal to, so the 90s cancel. and you get angle BCK plus or minus, I think it's minus that. Angle KCD over 2. Let's see what that looks like. Interesting. And KCD over 2 is QCD over 2, which yeah, so let's see. I think we're very close. Okay, so QDH is half of QCH, which is a quarter of ACH. So we want to show this is a quarter of ACH. Let's see. So BCK is BCH plus QCH. And then KCD, so yeah, I'll just write both of these. So this is BCK is BCH plus QCH minus, then KCD is BCH, well, it's QCH plus 2 BCH. Okay, so yeah, it simplifies a lot. Because once you divide by 2, then a lot of stuff cancels and you just get QCH over 2. And we want to show that, and that's QDH.
It is, yeah, it is QDH.
So that means that this means that DK and DO are orthogonal. And that means that K, O, and B are collinear. All right. Very cool. So that was fun. Kind of a long angle chase, but yeah, we used a lot of interesting things. We used that harmonic quadrilateral. We used spiral similarities, and that mostly finished it off. All right, so let's check out the next problem. This one looks like it might be kind of easy. So let's see if this one looks a little harder. So let's check it out. How do I maximize? There we go. So we have a triangle, and R is any point on arc BC. So yeah, it looked like a lot of information, but it really wasn't. Once you find the right things. So we have 2 points on AR. So we draw the ray AR. And some cyclic quad. We want BP, CQ are cyclic. So this would be P and this would be Q. And then BP and CP, we see where they meet the circle. BP, CP, interesting, BQ and CQ. Okay. So those points, this is PB, PB, this is PC, and then we have QB, and QC. And then we draw P, PB, PC, and Q, QB, QC, and we draw the centers of those circles. They almost look the same size, but I don't think it's true, but we'll see. So interesting. That looks like it might lie in the circle. So this would be OP, and the center of this almost looks like point C, but it's not. It is. Now that looks a little less like it lies in the circle. So maybe that was just a coincidence. We want to show A, OP. Yeah, they don't lie in the circle necessarily. We want to show A, OP, OQ, and R are cyclic. All right, let me make this look nicer. Okay. Yeah, it might overlap the problem statement, but oh well. Unless I shrink it a lot. Okay. And now it almost looks like OP lies on. It almost looks like that's like a trapezoid. Let's check. Yeah, I think it's really an isosceles trapezoid. Okay, that's interesting. So yeah, they're tricking us. And it looks like these circles are the same size. Let's see. So, yes.
If that were true, then QBQC should be equal to PCPB.
Okay.
If those two circles are the same, since
This
angle
equals this angle. Yeah.
they're not the same, but 180 minus each other. They're
Yeah.
supplementary, but the sine of that angle is still the same. So yeah.
It means, yeah, I see what you're saying. Because they're 180 minus each other, yeah, QBQC would have to equal PBPC. And PPCPB is similar to PBC. So you might be able to use that. And QC, I'm assuming, yeah, is similar to QBC. And yeah, and PBC and QBC are not similar, but they're like pseudo-similar. The angles out to, well, actually, what am I saying? I think it might just be law of sines that if you do it enough, you would get it. Well, yeah. I'm sorry, go ahead.
Can we angle trace that PCBP, that angle? PCPB. No, PCBP is equal to QBCQ.
QBCQ.
It looks like something which can be angle traced, and that would prove that QBQC is PCPB. You know, you just need to show that some angles are equal to have equal segments on a circle.
Yeah. It looks, yeah, like it might be able to be angle chased. Yeah, QBCQ. So QBCQ is the same as QBAC. Or QBBC actually. Now I'm confused. Or no, it's QBBQC. So yeah, it's like we want to show that this and this are isogonal. So if we look at angle PCB, if we look at this angle, we want to show that PB and C, we want to show that these two rays are isogonal, or this.
Oh, it looks like PBQC is parallel to PCQB, and it is also parallel to AP.
Yeah.
So now it looks like we have like a homotopy or something. Not necessarily, but something similar.
Yeah, I was gonna say like these whole things look congruent. BPCAPB and BQCCQB. So, and yeah, that's equivalent to all those being parallel.
Yeah, we have like some translation, which translates one circle to the other. But that is not so important.
Yeah, we just have to figure out what order to prove things in. Yeah, is it obvious that those are parallel?
I believe it's an angle trace, but I'm not exactly sure.
Yeah. Sure seems like one. Oh yeah, so showing that this is showing that they're parallel to AP is an angle chase. Because yeah, BQBPC is BCPC, which is BCP, which is BQP. So yeah, we know they're all parallel. If we know they're all parallel, then we know that this triangle is congruent to this triangle. And
yeah, then we have that like trapezoid thing. And also we know that those two circles are the same size.
oh, yeah, because if the triangles are congruent, then the circles are congruent. Yeah.
Yeah. But which triangles are congruent?
PCA, PB, and QBR, QC.
Yeah, that's true. But we basically have that QBQC is PCPB, and that proves that those two circles are the same size.
Oh yeah, it proves it in a different way. Yeah.
So now I think since we want to show that AOPOQR is also a isosceles trapezoid, I mean, we just noticed that it is that OPOQ is parallel to AR, but we want to show that it is isosceles to show that it is concyclic. Then we would want to show that the whole quadrilateral PCAOPPB is like congruent to
Yeah.
QCOQRQB.
It's trivial by symmetry because yeah, the whole problem is trivial by symmetry once we know this because PCA PB is congruent to QBR QC, and so I mean like everything is symmetric over the perpendicular bisector of AR, right? This circle and this circle are symmetric over. If this triangle and this triangle are symmetric over the perpendicular bisector of AR, then everything is. OP and QC are symmetric, or sorry, OP and OQ are, right? Everything is. So that kind of solves it, right?
Yeah, probably.
In fact, once you know the parallels, the whole problem falls apart. So yeah.
Yeah, and it looked like a hard problem.
Yeah, it looked hard, but it was actually very easy. So let's see. So angle BQB, angle BQBA. The hardest part of this problem is just writing all the indexes. BQBPC. I'm exaggerating, of course, but yeah. Is BCPC, which is BCP, which is angle BQP. Let me see. BCP, which is BQA. Yeah. And so that means that PCQB is parallel to AR. And then similarly, PBQC is parallel to AR. And that implies that PCAPB is congruent to triangle QBRQC. And both are reflections across the perpendicular bisector of AR. And that implies OP and OQ are reflections across the perpendicular bisector of AR. Oh, well, actually, yeah, I think I'm missing something because yeah, it's so OP. Yeah, I have to use that the circle passed through P. For some reason, I thought this was like the circumcircle of A PBPC, but obviously it doesn't pass through A, so I can't just say it's trivial. That but here's where that 180 minus comes in. So yeah, I do need that extra step. I thought it was just trivial right away. My bad. Okay. PBPC equals QC. So yeah, I know that those segments are reflections across the perpendicular bisector. Then I need to show that those circles are symmetric across the perpendicular bisector. And okay, so if I show they have the same size, then that shows that they are reflections, which is basically
I think that is not necessarily true.
that if they're the same size, then they're reflection. Okay, maybe not.
You have like two circles which have the same size for each segment, PC, PB.
But the thing is, the segments themselves are reflections across the perpendicular bisector. So this segment and this segment are reflections, and the circles containing those segments are the same size. So then the circles have to be reflections. I think that's right.
Maybe you could like more formally show that triangle PCOPPB is like congruent to QCOQQB.
Okay.
That is an angle chase. Very easy. Yeah.
Oh yeah, I kind of like that. So yeah, so PCOPB, we can write that that's a good way to do it. That is twice 180 minus PCP. Which is twice, that's twice angle B, that's 2 times angle BQC. Which is angle QBOQQC. Yeah, I gotta add a P here. All right. So that means that those triangles are congruent. And yeah, from there it's not hard. So and we know that because those segments are equal. And yeah, this implies that OP and OQ are reflections across the perpendicular bisector AR. And that means that AOP OQR is an isosceles trapezoid. And that means that AOP OQR is cyclic. All right. So yeah, that was an easier one. So I did pick one from the Taiwan team selection test. So this looks like it also might be a little easier. This problem is, yeah, not from IMOC, but it's from the Taiwan team selection test. Let's try it out. So we have a triangle. Let me just make this is bothering me a little bit. And let me break this into two lines. It's better. All right, so we have a triangle ABC with ortho